So within exercise 15 we are given a certain robot with the presented state space representation, and this is the given state. In the first part we were asked to simulate the robot. We already have the function f and we understand what is the state, so what we would do is we would use the Euler approximation in order to approximate the upcoming state of the robot, and we would pass the state of the robot to a certain schematization function in order to view the robot. So okay, so this is the code. Because we were asked to start from different initial contexts, I would change later on the initial input, which is going to be the same throughout the entire motion of the robot, from 1, which causes the robot to spin around itself, starting from going to the left, thus going into the anti-clockwise sense, and then for u is equal to minus 0.1, which allows the robot to go into the other sense, but in a slower manner. So this is for u is equal to 1. And this is for u equal to minus 0.1. Obviously the car is slower, but the orientation is now the clockwise orientation. Okay, for the next part we were asked to propose a heading controller for the robot. So what we've done is that we used this trivial controller over here. We would pass this function, the variable e, which houses theta bar minus the current theta of the robot. Theta bar is the desired theta, the desired heading. We can experiment with this code for theta bar being 0. And that's theta bar equal to pi over 2. After that we were asked to create a certain controller that allows the robot to track a certain straight line AB, and using this condition understand that it reached the point B, so it should stop. So what we've done is that we defined phi, which stands for the slope of the straight line AB relative to the x-axis, and then over here we have E. This E is pretty much this condition, but avoiding this inequality, this entity itself is very useful for the controller. So over here this is E, and this is theta bar is equal to phi minus math dot a tan of E. Then this entity theta bar would be passed over here in order to generate the control input. So we can test this code. for part 4 we were asked to do the same thing but for a sequence of lines which would form, if printed at the same time, a certain closed loop. So this is part 4. This is the sequence of straight lines, and as you can see over here, the end of a line is the same as the beginning of the upcoming line. And as for the control, it's the same as the control in part 3, but this condition which was presented in part 3 would be used to toggle through the straight lines. So let's try this code. Now for the part 5 we were asked to do the same thing presented in part 4 but with more than one robot, and the robots must have different initial states, and their speeds must be different. Also we must add a controller in order to avoid the collision. Okay, so what we've done is that we have defined this function collision avoidance, which takes the state of two robots. What it does is that it uses those states in order to calculate the Cartesian distance between those two robots. If the Cartesian distance is less than a certain safe distance, the controller would propose this control input, else it would propose nothing, because in the else category there is no need for avoiding the other robot. And here are the initial states of the robot, and this part is the one we've seen in parts 3 and 4. Okay, so what we've done is that we defined the code presented in part 3 and 4 for the robot 0 first, because we wanted to ensure that robot 1 is avoiding robot 0, and robot 2, you can see it over here, robot 1 is avoiding robot 0 and robot 2 is avoiding robot 0. This is enough given the fact that we used the following initial positions. We didn't need to make sure that also bot 2 is avoiding bot 3. And when it comes for the control, the thing is this collision underscore avoidance function, as we said, takes the state of the first robot and also the second robot, and what it does is that it generates the suitable input. This input would go into the overall input, which contains this controller's input that we've seen before, plus this extra part. And let's see the code in action. We could see over here how there's a correction of the heading of this in order to not hit this, and then everything just works smoothly because there's pretty much no need to avoid anything over here. each robot is moving in its specified velocity and is following the cycle.